So maybe let's talk about that a little bit, the world of ASICs, and
Yeah,
well, actually, you're you're you have a new role at SiFive. What's that place about? What is the vision
sure. So
for their vision for, I would say, the future of computing?
I lead the engineering and product teams at SiFive. SiFive is a company who's was founded with this architecture called RISC-V. RISC-V is a new instruction set. Instruction sets are the things inside of your computer that tell it how to run things. x86 from Intel and ARM from the ARM company and things like this are other instruction sets.
Sorry to interrupt. I've talked to Dave Patterson, who's super excited about
Yeah,
RISC-V.
Dave is awesome.
Yeah, he's brilliant. Yeah.
Yeah. The RISC-V is distinguished by not being proprietary.
Mhm.
And so x86 can only be made by Intel and AMD. ARM can only be made by ARM. They sell licenses to build ARM chips to other companies, things like this. MIPS is another instruction set that is owned by the MIPS company, now Wave, and then it gets licensed out, things like that. And so RISC-V is an open standard that anybody can build chips for. And so SiFive was founded by three of the founders of RISC-V that designed and built it in Berkeley, working with Dave. And so that was the genesis of the company. SiFive today has some of the world's best RISC-V cores, and we're selling them, and that's really great. They're going to tons of products. It's very exciting.
So they're taking this thing that's open source and just being trying to be or are the best in the world at building these things.
Yeah, so here it's the specifications open source. It's like saying TCP/IP is an open standard or C is an open standard, but then you have to build an implementation of the standard. And so SiFive, on the one hand, pushes forward and defined and pushes forward the standard. On the other hand, we have implementations that are best in class for different points in the space, depending on if you want a really tiny CPU or if you want a really big, beefy one that is faster, but it uses more area and things like this.
What about the actual manufacture chips? So like what?
Yeah, so
where does that all fit? I'm gonna ask a bunch of dumb questions.
That's okay. This is how we learn, right? And so, what the way this works is that there's generally a separation of the people who design the circuits and then the people who manufacture them. And so you'll hear about fabs like TSMC and Samsung and things like this that actually produce the chips, but they take a design coming in, and that design specifies how you turn code for the chip into little rectangles that then use photolithography to make mask sets and then burn transistors onto a chip or onto silicon rather.
So, and we're talking about mass manufacturing. So,
yeah, they're talking about making hundreds of millions of parts and things like that. Yeah, and so the fab handles the volume production, things like that. But when you look at this problem, the interesting thing about the space when you look at it is that the steps that you go from designing a chip and writing the quote unquote code for it and things like Verilog and languages like that, down to what you hand off to the fab is a really well studied, really old problem. Mm-hmm. Okay. Tons of people have worked on it. Lots of smart people have built systems and tools. These tools then have generally gone through acquisitions. And so they've ended up at three different major companies that build and sell these tools. They're called EDA tools, like for electronic design automation. The problem with this is you have huge amounts of fragmentation. You have loose standards, and the tools don't really work together. So you have tons of duct tape, and you have tons of lost productivity.
Now these are tools for designing. So the RISC-V is a instruction. Like, what is RISC-V? Okay. Like, how deep does it go? How much does it touch the hardware? How much does it define how much of the hardware is?
Yeah, so RISC-V is all about given a CPU, so the processor and your computer. How does the compiler, like the Swift compiler, the C compiler, things like this, how does it make it work? So it's what is the assembly code, and so you write RISC-V assembly instead of x86 assembly, for example.
But it's a set of instructions as opposed to...
set of instructions. Yeah.
Why do you say it tells you how the compiler works?
Well, it's what the compiler talks to.
Okay.
Yeah.
And then so the tooling you mentioned, the disparate tools are for what?
For when you're building a specific chip. So RISC-V...
In hardware.
In hardware, yeah. So RISC-V, you can buy a RISC-V core from SiFive and say, hey, I want to have run a certain number of gigahertz. I want it to be this big. I want it to have these features. I want to have, I want floating point or not, for example. And then what you get is you get a description of a CPU with those characteristics. Now, if you want to make a chip, you want to build like an iPhone chip or something like that, right? You have to take both the CPU, but then you have to talk to memory. You have to have timers, IOs, a GPU, other components. And so you need to pull all those things together into what's called an ASIC, an application-specific integrated circuit, so a custom chip. And then you take that design and then you have to transform it into something that the fabs, like TSMC, for example, know how to take to production.
Got it. So, but yeah, okay.
And so that process, I can't help but see it is a big compiler. Okay.
Yeah,
It's a whole bunch of compilers written without thinking about it through that lens.
Isn't the universe a compiler in that? Okay.
Like compilers do two things: they represent things and transform them.
Yeah.
And so there's a lot of things that end up being compilers.
Yeah.
But this is a space where we're talking about design and usability, and the way you think about things, the way things compose correctly, it matters a lot. And so SiFive is investing a lot into that space, and we think that there's a lot of benefit that can be made by allowing people to design chips faster, get them to market quicker, and scale out. Because the alleged end of Moore's law, you've got this problem of you're not getting free performance just by waiting another year for a faster CPU. And so you have to find performance in other ways. And one of the ways to do that is with custom accelerators and other things in hardware.
And so, well, we'll talk a little about a little more about ASICs. But do you see that a lot of companies will try to have like different sets of requirements that this whole process to go for? So like almost different car companies might use different and like different PC manufacturers. Like, so is RISC-V in this whole process, is it potentially the future of all computing devices?
Yeah, I think that, so if you look at RISC-V and step back from the silicon side of things, RISC-V is an open standard. And one of the things that has happened over the course of decades, if you look over the long arc of computing, somehow became decades old.
Yeah.
Is that you have companies that come and go, and you have instruction sets that come and go. Like one example of this out of many is Sun with Spark.
Yeah.
Sun went away. Spark still lives on at Fujitsu, but we have HP had this instruction set called PA RISC. So PA RISC was its big server business and had tons of customers. They decided to move to this architecture called Itanium from Intel.
Yeah.
This didn't work out so well.
Yeah.
Right. And so you have this issue of you're making many billion-dollar investments on instruction sets that are owned by a company. And even companies as big as Intel don't always execute as well as they could. They have their own issues. HP, for example, decided that it wasn't in their best interest to continue investing in the space because it was very expensive. And so they make technology decisions, or they make their own business decisions. And this means that as a customer, what do? You've sunk all this time, all this engineering, all this software work, you've built other products around them, and now you're stuck. Mm-hmm. Right. What RISC-V does is it provides you more optionality in the space, because if you buy an implementation of RISC-V from SiFive, and you should, they're the best ones.
Yeah.
But if something bad happens to SiFive in 20 years, right? Well, great. You can turn around and buy a RISC-V core from somebody else. And there's an ecosystem of people that are all making different RISC-V cores with different trade-offs, which means that if you have more than one requirement, if you have a family of products, you can probably find something in the RISC-V space that fits your needs. Whereas if you're talking about x86, for example, Intel's only going to bother to make certain classes of devices. Right.
I see. So maybe a weird question, but like if SiFive is like infinitely successful in the next 20, 30 years, what does the world look like? So like, how does the world of computing change?
So too much diversity in hardware instruction sets, I think, is bad. Like we have a lot of people that are using lots of different instruction sets, particularly in the embedded, the like very tiny microcontroller space, the thing in your toaster, that are just weird and different for historical reasons. And so the compilers and the tool chains and the languages on top of them aren't there. Right? And so the developers for that software have to use really weird tools because the ecosystem that supports it is not big enough. So I expect that will change, right? People will have better tools and better languages, better features everywhere that then can service many different points in the space. And I think RISC-V will progressively eat more of the ecosystem because it can scale up, it can scale down, sideways, left, right. It's a very flexible and very well considered and well designed instruction set. I think when you look at SiFive tackling silicon and how people build chips, which is a very different space, that's where you say, I think we'll see a lot more custom chips. And that means that you get much more battery life, you get better tuned solutions for your IoT thingy. You get people that move faster. You get the ability to have faster time to market, for example.
So how many custom? So first of all, on the IoT side of things, do you see the number of smart toasters increasing exponentially? So, and if you do, like, how much customization per toaster is there? Do all toasters in the world run the same silicon, like the same design, or is it different companies have different design? Like how much customization is possible here?
Well, a lot of it comes down to cost, right? And so the way that chips work is you end up paying by the one of the factors is the size of the chip. And so what ends up happening just from an economic perspective is there's only so many chips that get made in any year of a given design. And so often what customers end up having to do is they end up having to pick up a chip that exists that was built for somebody else so that they can then ship their product. And the reason for that is they don't have the volume of the iPhone. They can't afford to build a custom chip. However, what that means is they're now buying an off-the-shelf chip that isn't really good, that isn't a perfect fit for their needs. And so they're paying a lot of money for it because they're buying silicon that they're not using. Well, if you now reduce the cost of designing the chip, now you get a lot more chips, and the more you reduce it, the easier it is to design chips. The more the world keeps evolving, and we get more AI accelerators, we get more other things, we get more standards to talk to, we get 6G, right? You get changes in the world that you want to be able to talk to these different things. There's more diversity in the cross product of features that people want, and that drives differentiated chips in another direction. And so nobody really knows what the future looks like, but I think that there's a lot of silicon in the future.